Hello, everyone. We are going to look into chapter 3 or 4, exam number 4. So it is related with the interference, and as you know, the interference is based upon there's a two slit, and then the thin film, and there are two things. One is the AR coating, and then the soap film. And then there is a Newton ring, and then there is the Michelson interferometer. And then you need to know the most important thing is that interference is related with the two beam. So two beam interactions, two light beam interactions. And then you need to consider what is the path difference between the beam. And depending upon the path difference, if it is order over m lambda or m plus half lambda, you may get the constructive or destructive. And on the top of it, you may have to consider the phi phase shift in the reflected beam. N1, N2, N1 is larger, N1 is smaller than N2. And then there is a phi phase shift. And phi phase shift is in fact corresponding to half lambda path difference. So you have to consider whether there is a phi phase shift in this case. In the two slit, obviously, the D theta and the D sine theta sine lambda and the constructive and plus half lambda destructive. Air coating and soap film has a different structures, such as N1, N2, N3, such that you have a N1 is smaller than N2, and then N2 is smaller than N3. So in this case, you have a phi phase shift, and then you have another phi phase shift. So basically, it is the pi plus pi is 2 pi, so that basically between these two beams, there's no phase delay, phase difference. But in the case of a soap film, then you have a N1, N2, and then N1. Usually N1 is smaller than N2. So that there is a phi phase shift, and then refracted, and then reflected, and then coming out. So in this case, no phase shift because N2 is larger than N1. So that there is a phi phase shift between these two beams, so that there is already half lambda a phase shift. So that in this case, in the case of soap film, then you have a different cases. It's in the case of 2t. So usually 2t is m lambda, then is destructive. And m plus half lambda is constructive. So note that it is opposite. And the same as for the Newton's ring, you have a Newton's ring here. And then note that is n glass, glass, and glass. So that you have to think about that there is another diffraction, another reflection here. So that is air. So if you just blow up, there is a air, and then glass. Glass. So that there's a pi phase shift, similar to the soap film. So soap film, and Newton's ring shares the same physics. There is already pi phase shift. Okay. The Michelson, there is no those kind of considerations. Anyhow, just keep in mind these differences. Okay, so find the largest wavelengths of the light falling on double slit separated by the 1.59 micron, for each there is a second order maximum. There is a second order maximum. Okay, so we note that d sine theta is m lambda for the double slit. So you get the double slit. And then requirement existence of a maximum, it means the sine theta is always less than 1. So m lambda should be, in this case, m lambda should be larger and smaller than the d. So largest wavelengths for the second order m equal 2, then if you just put the m equal here, 2 lambda equal to d, so lambda max is equal to t over 2. D is given by here. So it's D, so that we get lambda maximum is this, which is 10 to the minus 6 meter. If the first order maximum for the monochromatic light falling on a double slit, once again, so double slit is angle of the 1.5 degree. What is the angle of the fifth minimum? Answer in radian. Okay, so condition for the maxima for the double slit is d sine theta m is given by m lambda. So depending upon m, you have a different theta. Okay. First order maximum is happening at the, this is the first order. The angle is 1.5 degree, so that m equal 1, and the theta is given here. And then for the condition for the minima is d sine theta is given by m plus half lambda, and the for fifth minimum order is max minimum order equal 5, and then the m equal 4, so that you can get this value. Okay, and then we note that lambda is d sine theta. Okay, so that you can find out theta 5. So note that sine theta 1 is already known here. And from this, you get the relationship between the lambda and the d. Okay, so in order to find out theta 5, we are going to utilize the relationship between the lambda and d. Okay, and then in this case, you get substitute lambda equal d here. So you just put t times sine 1.5 degrees, and then you get this relationship, and then sine theta 5 is this one, and then it is given by this one. So basically, the important one is here. So what is the angle of the fifth minimum? That means we have a m equal to 4 is the case. Okay, so note that it starts from the 0. Okay, 0, 1, 2, 3, 4, so that you get fifths. Okay, and then M should be the 4, not 5. For 360 nanometer light falling on double slit, once again, double slit is separated by this one. So this D is known, double slit. And what would be the distance between the fringes if the entire apparatus was submerged in the water? Okay, it's not in the air. So fringe spacing formula is given by delta y is given by this one. If you do not recall it, there is two slits, and then you note that so d sine theta equal m lambda, and then on this ym theta m. And then note that this is the distance between the L and this is the D, okay? And then here is the theta, is a small sine theta, tangent theta. So that what is happening here is that theta m is ym over L. Yeah. And then you get, here is the d sine theta in n lambda, d times theta m lambda, okay? And then you get ym is given by m lambda L over d, okay? So for the spacing, ym plus 1 minus ym is nothing but lambda L times d, okay? This is the formula you're going to use, okay? And then here is the tricky part, the wavelengths in the medium. So they did this in the water. The wavelengths in a medium is changing by this refractive index, okay? So that this is the vacuum, and this is the water. So here is the refractive index of water. And then delta y is given by this one. And I'm sorry for this one, but you get delta y, okay? Now we have a soap film with the refractive index 1.41 hanging in the air, reflects the dominantly red light with the wavelengths of this one. What is the minimum thickness of this film? So it's time to think about the phi phase shift in the soap film. So air to film reflection undergoes a phi phase shift. Film to air, there is no phase shift. So there's a constructive reflection condition now becomes this. Okay. So the minimum thickness is happening when m is go to be 0. So note that m goes to 0. And then 2nt is given by lambda, half lambda, such that t is this one. And then if you just plug in the numbers, you can get a t. And light wavelengths over 564 shines down on two glass substrate plates, spaced at one end by a thin piece of paper. Looking down on the plates, and the 25 bright interference fringes are observed across the top plate with dark fringes at the end of a paper. Okay, how thick is the piece of paper? So now it's time to think about once again. So you have a n glass n air, and then once again n glass. Okay, so the what's going to happen here is that we are going to first reflections, then this one. So we are going to talk about the interference between these two beams. So the phase, there's no phase shift when the light reflects at this boundary, because glass refractive index is higher than an air. But in this interface, diffractive index of a glass is higher than this one, so that you have a phi phase shift. Okay, and once you get the pi phase shift, 2t equal to m lambda becomes destructive. Okay, and then fringe counting, dark fringes at the thin end, m equal to 0 at t equal to 0 here. And then bright fringes, there are 25 corresponding dark intervals. Maximum order is 25. And thickness at the paper end here, T. And then here is the case. Okay, so that the 25 bright interference fringes, and at the end of a paper, so that at the end with the T, you get constructive T. Okay, so substitute the value for m equal to 25, and then you can get the result for T. Okay, so here is the case. So this is the one thing we need to know. What is the condition? And then dark fringes at the end, it starts from the m equal to 0. Okay, so that is going to be m equal to 0 at t equals 0. At the given 25 fringes, there are 25 corresponding intervals, and then the maximum order should be 25. So you need to count the right integer. It could be, sometimes it could be 24 or 25, but you need to figure out how to count the m. Okay, that's the key thing. And then in this case, m equal to 25, and then you just plug in the numbers for constructive. Note that at the t, it says the bright. Bright means it's the constructive, and that it's a bright condition corresponds to this, not this. Yeah, okay. So this is the same case as this one. Note that. But the dark fringes is 2t equal to m lambda. So note that 1t plus another t, so 2t is the path difference. And if the 2t is m lambda, and then it is destructive. Sorry, this is not destructive. And then you get all the numbers correct, and then you can find out t. So let me summarize. In this case, you need to figure out there's a phi phase shift. Okay, due to reflection from the air to glass. And then if there's a phi phase shift, 2t, which is the path difference, should be multiple of integer. This is the dark fringes. Okay, and then you need to count the m. And then in order to count the m, starting point is as m equals 0 at t equals 0. At t equal to the case, then you get m equal to 25. That's the key point. And then once you find out m, you go back to this formula, which is this, and then you plug in right numbers. So in the case of interference, it's absolutely important to find out what is the correct integer. So what is the minimum thickness of a coating so that it is so we have a 3-layer, and one is in the air, and two thin film, and then N3. So note that N2 is 1.38, 1.65, 1. So that in this case, there is no pi phase shift. Okay, that's the key thing. So that this is the path difference, and then it becomes destructive. Okay, so usually integer lambda becomes constructive, m plus half integer because destructive, as in the case of two slit. Okay. And we require destructive interference because it is anti-reflection, means there's no reflection due to destructive interference. And then in this case, you get this relationship, and then you can get a T. Okay? What is the smallest thickness of the soft film that would appear black? Soft film, once again, is a soft film, so that N1, 1.31. 1. So in this case, there is a 5 phase shift. Here, uh, yeah, okay. So there is a 5 phase shift, but there's no 5 phase shift, so that between them there's a 5 phase shift. So how the 5 phase shift is nothing but half wavelengths. So the condition for the minimum refracted light is in this case is the destructive. And then for smallest non-zero is m equal to 1. And then so for the thickness, you can get this one. And then plug in the numbers, you will get the thickness. And now you have a Newton's ring. And once again, Newton's ring has 5 phase shift because of the reflection from air to glass. There's a 5 phase shift upland path difference. Okay, so that there's a half lambda. Newton's ring conditions, dark fringe is 2 m lambda. So this is the very similar to the slope because of this 5 phase shift or half lambda. And then we need to, once again, 29 bright and 29 dark, so that in this case m equal to 29. And then we need to get the right m. Okay, so this is the right m. And then if you just plug in m here, and then you can get the t. What is the wavelength of the light entering Michelson interferometer if 355 bright fringes are counted when the movable mirror moves 0.14 millimeters? Okay, so mirror motion doubles the path range. So this is the, so if there is a, it's mirror one, to here. So in this case, it goes to the mirror and then come back. So that is the, as it says, mirror motion doubles the path changes. That's the key thing. Mirror displacement will change the path by 2D. And the fringe condition is that 2D equal to m lambda, in this case. And then solve for these cases, plug in the right number, D, and etc. Then you can get the wavelengths. And the light over wavelengths of a 560 nanometer passes through the two slits. So again, the screen is 2.5 meter away. A second source of unknown wavelengths produces second order bright fringes 2.12 millimeter closer to the central maximum than the 560 nanometers. What is the wavelength, the unknown? So fringe positions is related with the wavelengths. Okay. So fringe position formula, you get for the double slit, this is what he had in the previous examples. So here is the configurations. This is YM. And this is the D. And this is the L. Okay. This is a slit. And this is screen. So YM is given by this one. And then for the known values, well, lambda 1, D, L, we get M equal to second order, right? Okay, so that you can get the, by plugging this, you will find out what Y1 is given by this one, okay? And then position for the unknown wavelengths is fringe is 2.12 millimeter close to the center. That means Y2 is closer, means you should give a minus sign. And this is Y2 for unknown wavelengths. And then once again, we are going to modify this formula for the unknown lambda 2. Lambda 2 is given by this one. And then we are going to have the same M2 and then M equal 2. And Y2 is shown here. And then we can calculate the Y2. So it is a little bit complicated problem. The first thing you need to know the formula for the position of the fringes. This formula should be first found out, and then you need to know the position of the fringes, and then what it means by the closer to the central. That means Y2 is going to be minus this much. Okay, this is the key point. So that Y2 is now is this distance. And then once you know the Y2 distance, and then we note that D and L does not change, right? This is the same slit, same screen. So it doesn't change. And then only the Y2 will be determined. And then this is directly related with the lambda 2. Okay. 75. Thin film of soap coats a piece of a flat glass. How thick is the film if it reflects at 395 nanometer light most strongly when illuminated normally by white light? You cannot assume that soap is always soap film in air. So in this case, it's quite different. You need to figure out the difference. N1 equal to air, 1. And then there is a soap, and 2 is now 1.34. And then there is a glass, N3 is now is 1.52. So this is very similar to the AL coating. So when the light reflects, so N2 is larger than N1, so that there is a phi phase shift. And then it's refracted, and then once again it is reflected, because here glass is refractive index of a glass is higher than soap. You have another phi phase shift. Phi plus 5 is actually 2 phi. So that means there is no phase shift. Okay, so that the 2nt becomes m lambda is the constructive, not m plus half lambda, just in the soap cases. Okay. So you need to be very careful about the configurations, right? So for the constructive, now, even though we are using soap, because of the glass on the bottom, you get this condition for constructive, okay? Smallest non-zero is the m equal to 1, and then t can be found from this relationship. Okay, thank you.